Hi there. Today we are going to continue talking about hypothesis testing, and in this section we will look at how to conduct a hypothesis test to explore the difference between two proportions. In the previous section we looked at the difference between two means. We'll do the difference between two proportions in this section. So let's go ahead and dive in. Again, we will be utilizing the p-value method, and our one objective here is to learn how to perform a hypothesis test for the difference between two proportions. So to get started, let us just introduce an example to illustrate the type of problem where this method of hypothesis testing would be appropriate. The General Social Survey took a poll that asked 350 employed people aged 25 to 40 whether they used a computer at work, and 259 said they did. They also asked the same question of 500 employed people aged 41 to 65, and 384 of them said that they used a computer at work. So, from the two age groups, we can compute two sample proportions of the number of people who use a computer at work, right? So for the 25 to 40 age group, the sample proportion is 259 divided by 350, which equals 0.74. For the 41 to 65 age group, the sample proportion is 384 divided by 500, which equals 0.768. We can clearly see that the sample proportion is larger among older workers, but the question of interest involves the population proportions. There are two populations involved: the population of all employed people aged 25 to 40, and the population of all employed people aged 41 to 65. So the question here is whether the population proportion of people aged 41 to 65 who use a computer at work is greater than the population proportion among those aged 25 to 40. So in this example, we have two independent samples involving sample proportions, and the hypothesis test would be structured to do a comparison between the two populations. So let's go ahead and dive in here. Notation, right? This is all notation we've seen before, with the exception that because we're dealing with two populations, we use the subscripts 1 and 2 to delineate the symbols for each population, right? So P sub 1 and P sub 2 are the population proportions of the category of interest in the two populations. P1 hat and P2 hat are the sample proportions from the two samples. X sub 1 and X sub 2 are the numbers of individuals in the category of interest in the two samples. N1, N sub 1, and N sub 2 are the two sample sizes. And then, of course, to find these sample proportions, you take each X value and divide it by its corresponding sample size. So, the issue here is whether the population proportion of older people who use a computer at work is greater than the population proportion of younger workers. Okay? So in this case, we will be using P sub 1 to represent the population proportion of the younger workers, and P sub 2 would represent the population proportion of the older workers. Okay. The null hypothesis would be the assumption that there's no difference between the two proportions, right? That basically it would be the assumption that the population proportion of those who use a computer at work would be the same for both the younger age group and the older age group. And the way we would represent that in the null hypothesis is via the statement that says P1 equals P2. And then the alternate hypothesis with this kind of test, as before, it can be either a left-tailed, right-tailed, or two-tailed test, right? But the main thing to keep in mind is that the hypotheses are always set up as a comparison between the two population proportions. Now, once the hypotheses are established, then we find the test statistic, right? And this is the random variable in this case would be the difference between these sample proportions, which is p1 hat minus p2 hat. And when the sample sizes are large, this value, this difference between sample proportions, is a value that is approximately normally distributed, which means that the test statistic will be a z-score, a z-value, and it will be based on the normal distribution. The mean of the distribution is given by the difference between the population proportions. And then the standard error, or the standard deviation of this distribution, will be given by this formula here. Square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. And then, of course, the test statistic value is found by taking the random variable, which is this, minus the mean, which is this, divided by the standard deviation, which is this. Now, there is, okay, yeah, let me just, hang on a second. Yeah, let me just get my pen up real quick here. And color, I like to do black, so. So like what I was saying, basically, because it's based on the normal distribution, then the test statistic is random variable, which is p1 hat minus p2 hat, okay, minus the mean, which is p1 minus p2, divided by the standard deviation, which is the square root of p1 times 1 minus p1 over n1 plus p2 times 1 minus p2 over n2. Okay? So that is the formula for the test statistic. Now, there is a problem with this formula, and the problem is that P1 and P2 are the population proportions. This formula requires plugging in values for P1 and P2, but the population proportions are values that we wouldn't have. We wouldn't have access to the entire population to determine what those values are. So, what do? Well, first of all, remember that when we compute the when we compute the test statistic, we are always making the assumption that the null hypothesis is true. Which means in this case, we are assuming that P1 and P2 are equal to each other, right? Because that's what the null hypothesis says. If we assume that the null hypothesis is true, and if P1 equals P2, then P1 minus P2 is equal to 0, right? So in my formula here, I can replace the P1 minus P2 with 0. So that helps simplify it down, but it doesn't completely fix the problem because in the denominator, we also see P1 and P2 appear down there. So, again, so what we will have to do is we will have to replace P1 and P2 in the standard deviation with our best estimate of what both P1 and P2 are. Now remember, again, that at this point we are assuming that the null hypothesis is true, which means we assume that P1 equals P2, right? So when we replace P1 and P2 with our best estimate, we will be replacing both P1 and P2 with the same value, right? Because we're assuming they're equal to each other. The best value to use is this value that's referred to as the pooled proportion. which we just use the symbol p hat to represent that. And for the pooled proportion, we basically take both samples from both populations, combine them together, pool them together into just a single sample, right? And that represents our best estimate for both P1 and P2. So we add the x values together and divide that by the sum of the sample sizes. So in the formula for the standard error, in the denominator of this formula here, both P1 and P2 have to get replaced with P hat for the pooled proportion, which looks like this. And then I can simplify that a bit by pulling out a common factor of P hat times 1 minus P hat. And so when you make those modifications, then the formula for the z-score, or the test statistic, simplifies down into this. P1 hat minus P2 hat on top. And on the bottom, we've got the square root of P hat times 1 minus P hat times 1 over N1 plus 1 over N2, where P hat is that pooled proportion. Okay? So that's the formula we will use for the test statistic. The assumptions that need to be followed, really the same assumptions we made for the confidence interval, but this time we have to apply them to both populations. We have to have 2 independent simple random samples. Each population should be at least 20 times as large as the sample drawn from it. The individuals in each sample need to be able to be divided into 2 categories, and both samples should contain at least 10 individuals in each category. So here is the step-by-step procedure we would follow for conducting the test. Start by stating the null and alternate hypotheses. Choose a significance level alpha. Third step, compute the test statistic using this formula for z, and p hat is the pooled proportion, which we find by adding the x values and dividing by the sum of the sample sizes. Once we compute z, then we just find the p-value. Because the test statistic is a z-score, then the p-value will be the area, an area from the standard normal curve, which we can find either using the table or the calculator. If it's a left tail test, the p-value is the area to the left of z. If it's a right tail test, the p-value is the area to the right of z. If it's a two-tailed test, the p-value is the sum of the area to the left of negative z and to the right of positive z. Interpret the p-value. If making a decision, reject the null hypothesis if the p-value is less than or equal to the significance level alpha, and then state a conclusion. So let's go back to our example. The General Social Survey took a poll that asked 350 employed people aged 25 to 40 whether they used a computer at work, and 259 said they did. They also asked the same question of 500 employed people aged 41 to 65, and 384 of them said that they used a computer at work. Can you conclude that the proportion who use a computer at work is greater among those aged 41 to 65 than among those aged 25 to 40? Use the 0.05 level of significance. First, it's a good idea to check our assumptions. We do have 2 independent random samples from 2 separate populations. The populations would be the population of all workers aged 25 to 40 and the population of all workers aged 41 to 65. Those are both very large populations, definitely more than 20 times as large as the samples. The individuals in each sample are divided into 2 categories, right? Those who use a computer at work and those who don't. And each case, there are more than 10 individuals in each category, so all of those assumptions are satisfied. The next step is to establish the hypotheses. One thing I do want to make a note of is one thing to be careful of is setting up the alternate hypothesis correctly, right? You'll notice that it's set up as a left-tailed test, and that might be a little counterintuitive, right? Because in the problem description, we do see the word greater appear right there, and usually, historically, most of the time when we've seen a word that like suggests a greater or an increase, that has typically corresponded to a right-tailed test. The reason that this is a left-tailed test is because P1 here, that represents the population proportion for the younger age group. P2 represents the population proportion for the older age group. And the hypothesis test is supposed to be set up to see if P2 is greater than P1, right? And another way of phrasing that is by saying P1 is less than P2, right? So when we're doing a comparison between two populations like this, you have to be a little bit more careful, right? Because you have to make sure that the direction of the inequality symbol matches how P1 and P2 are defined, right? If P2 represented the older age group and P1 the younger, then it would be right-tailed, right? So just read it carefully and set it up the right way, okay? Once you have your hypotheses established, then compute the test statistic, right? And we have to compute the pooled proportion separately by adding the x values, adding the n values, and dividing. So the pooled proportion is about 0.756471. In the formula for z, we've got p1 hat minus p2 hat. On the bottom, we've got p hat times 1 minus p hat times 1 over n1 plus 1 over n2. And that gives me a z value of negative 0.94. Because it's a left-tailed test, the p-value is the area to the left of negative 0.94. And if we use the table to look that area up, it would just be the standard normal curve table. We would find this area to be 0.1736. And that p-value is definitely greater than 0.05. So we would choose to not reject the null hypothesis at the 0.05 level. And we would finish by saying we cannot conclude that the proportion of workers aged 41 to 65 who use a computer at work is greater than the proportion among those aged 25 to 40. And yes, you can also use your TI-84 to do this test. It's actually pretty straightforward. You would want to go to the Tests menu, press the Stat button, highlight Tests, and you want to scroll down until you see a function that's labeled to-prop-z test. And then it's pretty straightforward. From there, you just enter in the information it requests, right? So you type in your x1 value and your n1 value, right? So my x1 value was 259 in the example we looked at. N1 was the first sample size, which was 350. X2 was 384. The other sample size was 500. In the example we did, it was a left-tailed test. So the middle option there is for a left-tailed test. Select Calculate. It gives you a readout of lots of information, but the most important number there is the one labeled P, which is your p-value. And then we can take that, compare that to your value of alpha, right? So that's a pretty straightforward way to do it if you have the TI-84. Minitab also allows you to do hypothesis testing. We can't cover everything in this class, so we don't really go over Minitab, but if you use Minitab, this is the readout you would see. And again, it also gives you a p-value right there. So that wraps it up for this section. We've looked at how to perform a hypothesis test for the difference between two proportions using the p-value method. And thanks for watching this.